Hello everybody, welcome back to the Data Structures and Algorithms Specialization. Today we're going to be talking about what really goes into computing runtimes and really understanding how long it takes a program to run. So, in particular, today we're really going to dive in. Up till this point we're using this sort of rough number of lines of code executed count. And today we're going to talk about how accurate this is and what sorts of complications come in. And in particular, we'll see that if we actually want something that's sort of fundamentally an accurate measure of runtime, it's going to be a huge mess. We're going to have to bring in all sorts of extra data that aren't really convenient for us. And so we'll really sort of be talking about a problem that comes in with computing runtimes and algorithms, something that we're not going to resolve really until the next lecture. Okay, so to start with, let's look at this algorithm that we had for computing Fibonacci numbers. Remember, we created an array, we assigned the 0th element to 0, the first element to 1, then we had this big for loop where we set the ith element to be the sum of the I minus first and I minus second elements, and then at the end of the day, we returned the nth element of the array. So we determined that when we ran this program, we executed about 2n plus 2 lines of code, but we should really ask ourselves, is this number of lines of code executed really sort of an accurate description of the runtime of an algorithm? And, somehow, implicitly, this measure of lines of code assumes that sort of any two lines of code are sort of comparable to each other. They're sort of one basic operation. And so let's actually look at this program in some detail and see what goes into some of these lines of code and see how valid this assumption is. So to start with, we create this array. And what happens when you try to initialize an array? Well, this depends a lot on your memory management system. Fundamentally, all you have to do is you have to sort of find some space in memory and then get sort of a pointer to the first location. On the other hand, how exactly you find this, maybe you need to shuffle some other things around to make room for it. Maybe after you allocate the array, you then want to zero out all of the entries so that you don't have junk sitting in there. And so it's not entirely clear. It depends a little bit on how exactly your program is being interpreted. But it could be pretty fast. It could actually take a while depending on circumstances. Okay. Let's look at the next time. This is just a simple assignment. We set the 0th entry to 0. However, if you really look at this at the machine level, you're doing a bit more work. You need to load up the pointer to the 0th element of the array. You maybe then have to do some pointer arithmetic. You then need to store this literal 0 into that spot in memory. It could actually be not one operation, but a few operations. Similarly, when we set the first element to 1, you have to do sort of this very similar set of things. Next, there's this for loop. And with the for loop, again, every time you execute it, you have to do a few things. You need to increment the value of I. You then need to compare I to n to see if you need to break out of the loop. And if it is, you need to branch. You need to move to another instruction in your program after the for loop. Next up, there's this addition step. And here we have to do some things. We have to look up two values in the array. We have to write to a third value in the array. All of this involves the same sort of pointer arithmetic and memory lookups and writes that we were talking about before. But we also have to do this addition. And if it were just a normal addition, maybe it wouldn't be such a big deal. However, this is an addition of two Fibonacci numbers. And if you'll recall from a couple of lectures ago, we found that Fibonacci numbers were pretty big. In fact, so big that they probably don't fit in a single machine word. So adding two of them together actually takes a non-trivial amount of time. So somehow, not only do we have to do all of these array arithmetic things, but the actual addition of the Fibonacci numbers is actually a pretty non-trivial operation. Okay, and then we do this return step where we have to do an array lookup, which involves all the sorts of things we've talked about already, and then have to do a return, which sort of is going to operate with the program stack and sort of pop it up a level and return an answer. So, in conclusion, this program has 6 lines of code to it, but the amount of work being done in various lines of code is very, very different. Exactly what goes into each line of code is not sort of at all the same thing. Maybe we want to reconsider this count that the number of lines of code is sort of our runtime. Maybe we need to measure something else. So what else should we do? Well, if you want to be totally correct about what we actually care about, what you need to say is, well, we're going to take this program, we're going to run it on some real-life computer, and we'd like to know how much actual time it will take for this program to finish. Right? That is fundamentally what we want to know. Unfortunately, in order to figure that out, we need to know all kinds of messy details. We need to know things like the speed of the computer that we're running it on. If you run it on a big supercomputer, it'll take a lot less time than if you run it on, your cell phone. The system architecture of the computer will matter. Exactly what operations your CPU supports and exactly how long they take relative to one another, those are all going to have an effect on your runtime. The compiler being used is also going to make a difference. In practice, what you'll do is you'll write this program in some high-level language in C or Java or Python or something, and then you'll run it through a compiler to turn it into machine code. And then the compiler, though, isn't just sort of doing something completely obvious. It's performing all kinds of interesting optimizations to your code. And which optimizations it performs and how they interact with exactly what you've written, that's all going to have an impact on the final runtime. Finally, you're going to be